Hello, I'm Dave Tabb, and today I'd like to take you on a quick walk through some essentials in metabolomics. Specifically, how do we generate tandem mass spectra, or very energetic mass spectra, from metabolites, and then how do we interpret them, how do we match them to identities, and perhaps even quantify them. So we'll start with the classic GCMS, Gas Chromatography Mass Spec, and from there we'll move on to the subject of metabolite identification. I talk about GCMS as a classic because it's been around for decades. It is not the only way that we go about generating metabolite spectra, but it is a very dominant method and very much worth knowing about. And it's worthwhile talking about how this MS aspect of it has changed quite a lot in recent years. So from there, I'm going to start on a bit of a theoretical exploration at first of what's required for us to identify a metabolite. So we'll start with basic information about just the precursor ion, just about ions prior to any collision-induced dissociation or electron impact, and the retention times that they have from chromatography. Is it enough, based on an intact mass and a chromatographic retention time, for us to identify a compound? From there, we'll start talking about what is by far the most common practice, matching mass spectra and tandem mass spectra to mass spectral libraries. This is the dominant way that we go about identifying metabolites by MassBank. And from there, we'll talk about different sources from which we can draw these mass spectral libraries. And if the camera jogs, it's because my cats are in a fine mood this morning. So let's see how this goes. So we start with this lovely diagram from Stefan Neumann's office. He's a really great metabolite mass spectrometrist. So gas chromatography pushes metabolites through liquid at high pressure and temperature. Now I think that the way that I've written this headline is a little confusing, really. What we're attempting to do is put metabolites into the gas phase because they're quite volatile. So they're going to be in gas phase, moving through chromatography, then they reach they reach the mass spec by way of electron impact ionization. Now, the chromatography that we're using here is quite distinct from what we would expect to see in LCMS. You know, maybe you have an analytical column that's just a few centimeters long in that case. But in the case of gas chromatography, though we're still using fused silica and still using pretty narrow inner diameters of less than a millimeter, we may have a length as high as 30 meters of analytical column. So the gas is moving not just through this very short distance and causing a separation. Instead, it's moving through 30 meters of this gas, causing a separation as the metabolites interact with their environment and finally pass out the other side. The temperatures we're talking about are pretty extreme. I've seen stuff approaching 400 degrees Celsius. That is obviously a high enough energy of a high enough temperature that a lot of extra chemistries become possible for these metabolites. So the mobile phase in this case is typically something like helium gas. Helium is not going to react with your metabolites, at least. And the stationary phase is not a bunch of beads in there. Instead, it's sort of an immobilized liquid coating to these 30 meter columns. So we have a gas rushing past liquid, and the metabolites in that gas are interacting with or not interacting with this liquid content for these columns. Okay, so from there, we can start thinking about what the environment is like inside a gas chromatography. So we call it a volatile environment because literally we're expecting our metabolites to be volatile in nature. They need to enter the gas phase. So when they're in this gas phase, they are able to, the stresses that they're under require that these metabolites be altered in some ways to reduce the amount of chemical interaction that they experience with their environments and with themselves. Because naturally, 400 degrees is not an in vivo environment, right? This is not the temperature our bodies walk around at. So you could imagine at 400 degrees a lot of chemical reactions inside the molecule itself become possible. So if we had the situation where reactions were taking place in the course of GC, the signal for this metabolite will now be split across multiple molecular forms. And this means that we would, in order to quantify the signal for the metabolite in its original form, we would need to add together all the metabolites, the submetabolites, secondary metabolites that formed in the process of GC. It's not a good arrangement. We would really much prefer that each metabolite that enters the column is the same metabolite as it exits the column, and that we don't need to worry about the splitting of signal to different secondary metabolites. Okay, so this is why we need derivatization. Derivatization is really important for us in preventing chemistry, the 400-degree chemistry happening to these metabolites, allowing them to pass through this very hot environment unchanged. All right, so there are plenty of chemistries that have been put forward for derivatization, but I wanted to focus on two that are quite common. We have two different challenges in this derivatization. One is that we need this metabolite to enter the gas environment. If the molecule can't be coerced into a gas at 400 degrees, we're not going to see it. We're not going to be able to separate it. So oxidation is one way that we can volatilize these molecules. So in this case, we have a double bonded O, so a carbonyl, that's being turned into a double bonded NOH. So that is increasing the likelihood that this glucose enters the gas phase. But we must also protect the molecule from further changes. So for this, we're going to use something called silylation. And that basically means sticking on a bunch of silicon atoms with methyls attached to them. Okay, I'm going to kick the cat off of the microphone stand. Okay, go away, cats. Thank you. All right. So now we have all these little OHs here, and they're a bit of a problem because at 400 degrees, those little guys can react. So we need to block these off in some way. What we see in silylation is that each of these OHs has now become a silicon with three methyls, with a trimethyl attached to it. So we started with glucose. We produced glucose oxime, and then produced glucose oxime, the 6-TMS derivative. These are the TMS, the trimethyl silicons. So you might ask the reasonable question, if we measure glucose oxime 6-TMS as our metabolite in the mass spec, how much does that resemble the quantities of the metabolite that we started the derivatization process with? And in the case of 6-carbon sugars, how many different 6-carbon sugars go through this process and look identical afterwards? So they were different sugars coming in, but one structure, this 6-TMS structure, afterward. So it may be the case that the derivatization process is going to turn molecules that had slight chemical differences into something that's all one thing. That can cause us problems when we're trying to quantify all the different 6-carbon sugars that were in the sample to begin with. It's happy to say, it's kind of happy talk to say, whatever your metabolite, of course we can ionize it. The reality is that we have differential success in producing ions that are suitable for GCMS, and the types of bonds that they contain are a pretty good indicator for us about what's going to fly and what isn't. So we start with class 1, the metabolites that contain hydroxylic and carboxylic functional groups, sugars, fatty acids, and organic acids. This is all good. So getting these guys to fly and to be protected in the course of GCMS can be thought of as a solved problem, but there are always ways to refine it. The next class is stuff that contains amine or phosphoric functional groups. I really like the way that this paper put it, that Yes, you can volatilize and protect metabolites that contain amines and phosphoric functional groups. And yet, if your method is being a little fussy with you, the molecules you're first likely to detect those problems in will be this class 2, not class 1. The class 1 ions, generally, so long as the moon is not in the incorrect phase, are going to work. But once we get to class 2, things get a little iffier, and you really want everything working properly with your experimental apparatus in order to get good ions from these molecules. And then finally, we get down to metabolites that contain amide, thiol, or sulfonic functional groups. The read, again, that I took from this paper at the bottom is that we're working on methods for these, and we have some methods that give us some limited success in that area, but sometimes they cause us problems. So an expert in dealing with these types of metabolites can probably get good results. Bart, I want you to stay away from the camera tripod, if you will. Thank you. All right. So this brings us to electron impact ionization, or sometimes just electron ionization. When we do GCMS, these molecules in derivatized form are coming off this very, very high temperature column, but unless they're ionized, we're not going to see them in mass spectrometry. So we must ionize these things, and the most common process we use for that. Bart, please get off of the tripod. Thank you, buddy. Okay, so electron impact ionization has been our best friend for this process. It's going to both produce ions and cause fragmentation. So this is a little unusual. If you're accustomed to thinking of electrospray ionization as something that just makes ions but doesn't really Zorch the ions passing through it, you have to think about it quite differently in the case of electron impact ionization. So here we have this common problem. So I would ask you to think for a moment back to your physics class in college. How do we make X-rays? Well, we shoot a beam of electrons at a metal plate, and that metal plate releases X-rays. So that should prove to you that an electron beam can carry a lot of energy. In this case, this beam of electrons is going to interact with the ions coming in from GC. That process is going to certainly ionize them and probably blow them apart in some important ways. So commonly, molecules will undergo first a loss of neutral molecular fragments, say throwing off water or whatever, if that were feasible in the chemistry, and eliminate... Daisy, would you please stop chewing on that knob? Thank you. An elimination of a charged radical. This is just as ETD in peptides can create a charged radical that then causes the breakage of bonds. You can have the creation and elimination of charged radicals through EI, and an intermolecular rearrangement. So having broken one bond can lead to a reformulation of the structure of the pieces that remain from it. Critically, electron impact is an in-source dissociation. This is quite different than the case of ETD, which is something happening after the ions are already in the instrument and you have just a relatively homogeneous population in the MassBank. In this case, electron impact is going to cause the breakage of these ions as it ionizes them. So there's no point at which we can capture the precursor ion and subsequently break it because it's already been busted at this first process. So electron impact is both ionizing and fragmenting metabolites as they come off GCMS, off GC. Now that's not the only option. We do have some chemical ionization methods, but it seems that the GC-EI-MS approach is really the most common that you'll see. All right, so all told, we have some process by which we are injecting our samples into these long columns, these millimeter long columns. We have a transfer line that's also doing this electron impact, that's creating fragments from whatever's passing. Then we have maybe an ion trap or just a quadruple, either way, that's measuring what ions are being produced at this moment in time. this is a pretty simple arrangement. If you're accustomed to looking at things like orbit traps and stuff like that, we have all these nice hybrid mass analyzers and so on that combine different mass analyzers in series. But this is a pretty straightforward arrangement. GC and a single mass analyzer type on the back end. This is not the only option, but let's just remember then that the MS scans that we produce from this are going to contain a mix of fragment ions and intact ions. It is possible that electron impact doesn't completely obliterate this precursor after all. So you may have some amount of unfragmented precursor effectively, and the fragments that are produced from it. Okay, now quite commonly we see single quadrupoles used here. These machines are very, very hard to kill, so you'll see some of these things from the 1990s still running in some core facilities. And it's a very low-cost option. The manufacture of quadrupole and ion trap instruments is much less expensive than these high-end Fourier Transform based instruments. These days, though, we will sometimes see time of flight or Fourier Transform Mass Specs, or even instruments that are capable of performing subsequent rounds of tandem mass spectrometry that can accept the input coming from electron impact. So there's the possibility that you would have accurate masses for the original metabolite and for the fragments produced from it, highly mass accurate data if you're using a TOF or an FTMS. Or you might choose the largest, the most intense ion from EI and say, I want to look further into that, set it up for further fragmentation and measure the fragments from that ion. So MS is also possible here. These are really important in changing the scope of what's feasible in metabolomics. Just as an aside, imagine that you have an ion that doesn't fragment to a wide diversity of fragments. If you have 3 or 4 fragments from a metabolite, yes, you can probably identify it, but you could boost your confidence in it if you had greater fragmentation within it. So you may need to cause subsequent fragmentation in order to get a more complete certainty about the identity of this metabolite. Okay, and certainly, just as in proteomics, we sometimes see in metabolomics that we have too complex a mixture for us to deal with in just a single GCMS-MS experiment, or GCMS experiment. So in cases like that, you might end up using a 2D separation. So have a separation to different fractions before you ever got to GCMS. That is also feasible here. It increases the amount of instrument time you spend on each sample, but you should be able to see deeper into the set of metabolites that it contains. Now, from there, I'd like to take us into the challenge of how we go about identifying compounds. So, I want you to imagine that we have conducted a GCMS experiment, and now we have a mass that we know very accurately because we had a TOF analyzer or a Fourier Transform analyzer. We've now measured this ion to have a mass of 500 Daltons. We believe that is accurate in this case within 5 ppm because of the type of mass spec we measured it on. Is this enough for me to identify it? So I would start by saying one of the benefits that we can get from highly resolved, highly mass accurate measurements is that we may be able to get the chemical composition of the compound. Now, a composition is not the same thing as an identity, right? So we have a mass. From that, we might be able to go to how many carbons, hydrogens, oxygens, nitrogens, phosphorus, and sulfurs does it contain. That's really good information, but is that an identity? Not yet, not yet. So let's then ask, can we get the composition from this? So in this case, in our highly mass accurate GCMS experiment, we've now said this ion has a mass of 500 Daltons plus or minus 5 ppm. This paper from Tobias Kind and Oliver Fien put together some simulations of this problem, and what they found was that this scenario means that we have 115 different chemical compositions that correspond to this mass. But they note that if you remember, if you measure the isotope packet that comes with this intact ion, you can probably use that information to trim down these compositions even to a much smaller set. So here they computed that starting with 115 potential compositions, they were able to cut that down to just 33 if they used the relative intensities of the isotopes. Good. So now we're able to get much closer to not an identity, but a composition that we think is most likely for this ion. But is that enough? So in this case, we're looking at the example they worked for C15H12O7. This was a particular metabolite they were interested in. So using that composition, if you go into databases of chemical compounds, how many possible compounds meet that C15H12O7 composition? Well, if you're dealing with something like chemical abstracts with 24 million entries back in 2006, they found 181 different compounds that all matched this chemical composition. When they went to the Beilstein database, they found 166 compounds with that structure, with that composition. Sorry. The Dictionary of Natural Products, they found 129, and you can see as you move down the list that as the database size of all compounds gets smaller and smaller, the number of compositions that match exactly with this elemental composition shrinks as well. So I guess the take from this is that an intact mass, even if you know its mass very accurately, and even if you know the isotopic the isotopic envelope very well, you may yet not be able to get to a single composition, and even a single composition is not enough to get you to a unique identifier. So this leads us to why fragment ions are so important. Having fragment ions means that you can be far more sure that you have the correct metabolite identity. We're not just going to base this off of an intact mass or its isotopes. Now we're going to use fragments. So in this case, I'm looking at a reference spectrum. This is one that was collected by the National Institute of Standards and Technologies in the United States. So they have a nice reference spectrum for a molecule that we showed just a few slides ago. We were talking about how we derivatize glucose. So this is glucose oxime 6-TMS, so the trimethylsilylated oxime ion of glucose. So what we see are a pretty solid list of fragment ions that should be seen if you've got a really clean spectrum of glucose, the glucose derivative. So the standard way that they go about doing identification from GCMS experiments then is to use spectrum library search. So in this case, we need to have an annotated spectrum library. And this is something you can purchase commercially, or that may have come with your instrument when you bought it for metabolite purposes. So these spectral libraries should contain hundreds of thousands of spectra at a minimum, I would hope. And when you're doing a spectral library search, you're asking for an experimental GCMS spectrum. Which spectrum in this library bears the greatest similarity to the experimental one that we calculated? We'll talk about the algorithms for that in just a moment. But we need to compare then against thousands of different entries in the library, which of these is most similar to what we recorded on our mass spec. There's a bit of a challenge, however, that makes this rather different than spectral library searching in proteomics, because in LC-MS of peptides, we have isolated ions of a particular precursor mass to charge value and then fragmented it. In this case, however, we have generated our mass spectrum via GCMS with electron impact. As a result, we don't have the precursor ion. We never isolated it. We just fragmented everything coming off of the GCMS at this moment in time. So our MS from GCMS is going to contain fragments, but may give us very little information about the precursor. So just to use about the ion, what ion was there before EI blew it apart. So in this case, this compound has an intact mass of 628.2572, but the spectrum doesn't even go that high. So the intact form of this ion is not available to us. We just have the fragments from it. So using fragment ions and what we know about the retention time for chromatography may give us the option of getting a really good hit in a spectral library. Now, I mentioned the NIST Spectral Library because it's the one I'm most familiar with, but there are plenty of other options, and we'll talk about those in just a minute. But since 1988, the NIST Electron Impact Spectral Library has been growing and growing. It actually started out as coming from EPA, the Environmental Protection Agency, and a bit of a one from, I believe, the FDA. But since that time, the NIST has been organizing this library. So it's very much been their big project for a long time. So in 2023, they made their most recent release at the time of filming for this library, and you can see that 347,000 different compounds are included in this library. That's a mammoth monster. Now, can you just download that? No. You can purchase the GCMS libraries and the LCMS MS libraries through a lot of different distributors. Typically, that's going to be on the order of like $3,000. So it's not cheap to get these very large libraries, but it's quite essential if you're producing lots of GCMS for unknowns to be able to identify them through spectral library matching. And what they mention here is that 85% of these compounds now have expected retention time indices, which is to say that if you had these 500 compounds appearing in your sample, you can order them at least in what retention time they should come off of the GC. You can map that to your retention times from your instrument. Maybe you did a 3-hour experiment, maybe you did a 1 hour, right? These are all very different things, but you can use these retention time indices to figure out the ordering in which these ions should appear in your MassBank. Okay, so they've produced a separate MS library. So if you're doing LC-MS instead of GCMS, you can get a library of 51,501 compounds. So that's a pretty good coverage for metabolites. Not as broad as the set of metabolites that are registered in the EI library, but if you're doing LC-MS, obviously you need LC-MS spectra, not EI spectra. Okay, so they've got two different kinds of search modes that are available in the software that accompanies this library, and it's worth talking about both for just a moment. So we start with the NIST MS software. The intent here is that we're going to compare spectra that we've collected experimentally against all corresponding members of the spectral library. The NIST MS software does that for us. So this is lovely when what you're capturing is a metabolite that exists as a perfect match in the NIST library. But what happens if the compound you've measured in your mass spec differs by, say, a single methyl versus what appears in the NIST spectral library? In LC-MS, you wouldn't even attempt to identify that spectrum by comparing it to the corresponding unmethylated sequence because it's got the wrong precursor mass. And in the LC-MS library, you're going to use that precursor mass to help you figure out which spectra are even comparable to your metabolite. Okay, so hybrid search allows you to look for one-offs, essentially, to say that I have this spectrum that I've captured experimentally, and it's not the same compound as the one in the spectral library, but if I add 14 to it, I've now accounted for that methylation, and now I get a perfect match between what I observed and what I saw in the database. That's a hybrid search. It's a form of blind modification searching, in essence, to say this metabolite plus some sort of adduct gives us what we measured experimentally. Okay, so this library is available from lots of vendors worldwide. The spectral library for LC-MS is going to cost you maybe $600, and something like the whole electron impact library will probably be many times that. So it's a purchase that you make because you're going to make a serious investment in metabolomics. it's also worth talking about how we go about saying this spectrum we captured experimentally is a match for this one in the reference library. How would you make that decision? Now, obviously in database search for proteomics, we have a very wide variety of algorithms used for saying how similar is this to this. We use cross-correlation, we use match counting, we use all kinds of interesting transformations of the data. But in the world of metabolites, the dot product or cosine similarity has become a very standard way of doing so. So to start, I would ask you to think of the spectra we collected as having 500 locations where a peak might be. So we're going to say if it fell at mass to charge 1, then anything up to from 0.5 m over z to 1.5 m over z just counts as a peak at 1. And I can keep doing that all the way up to 500 m over z. So for a range of 500 mass to charge units, I have 500 places where a peak might appear. In this model, we treat this as a 500 dimension space. So any spectrum is going to have its coordinates for each of these 500 dimensions supplied by the intensities at each place. So if I have a peak at 200 in this mass spectrum or tandem mass spectrum, in dimension 200 I have a coordinate that corresponds to that intensity. What comes out of this is that each spectrum can be perceived as a vector in space. All right, so I know I said it was 500 dimensions. We can think of it as just 2 peaks for the moment if that's easiest for you. So imagine that I am only monitoring intensities at 200 and 300. So 200 becomes my x-axis, the peak at 200 becomes the x-axis, the peak at 300 becomes the y-axis. Now a spectrum that has a very high intensity at 200 but a relatively low intensity at 300 stays pretty close to my x-axis here. But a peak that's a spectrum that's got a lot of intensity at 300 but very little at 200 is up here. So spectra that have comparable proportions at 200 and 300 would point very close together in this space. So the cosine between them is very close to 1 because the angle between them is very close to 0. This is what the math of the dot product gives us. So we can compute that really quickly. Basically, for each of these bins of m over z, we need to multiply the intensity that we observed in our mass spec by the intensity predicted at this site by the spectral library entry. At m over z2, we do the same thing. At m over z3, we do the same thing all the way up to 500. So we have those products and we sum them all together. And at the same time as we've been progressing through this comparison of intensities between the experimental and reference spectrum, we are also computing a running sum of squares for these. So having added these values together, we square root these intensities, square root these intensities, multiply those together, and out pops the cosine of this angle. So a cosine of 1 means that these two spectra have very, very comparable intensities. A spectrum cosine of 0 means that these spectra are just about as far apart as they could be. Okay, so this approach, well described in this wonderful paper back in 1994, that was really influential in my understanding how this works, becomes a very standard way for us to compare an experimental and a reference or library spectrum. So there are obviously plenty of ways that we might want to refine this to reflect the type of mass spectrometry we've done. So let's start with the idea that the MS has, because we did this in, say, LC-MS-MS, we have a precursor mass to charge value. If we have that, then we don't need to compare every spectrum in the library to the one that we collected on our instrument. We only need to consider those library spectra that match the precursor mass very, very accurately. So we can cut out a huge swathe of these comparisons to library spectra if we know what mass we blew up to create this MS-MS. Similarly, you might have very accurate mass measurements. If that's the case, for something with like less than 10 part per million mass accuracy, we may need to split up our bins that were 1 m over z wide to be much thinner than that. So you could, for example, say, my bins are now 0.01 mass units wide instead of 1 mass unit wide. That means that we increase the number of dimensions in our dot product computation, but there's a much better chance that we resist matching two peaks by random chance rather than because they represent the same ion. Okay, third, what if most of the intensity in this spectrum shows up in 1 or 2 peaks and the rest of the fragments are down in the grass? Well, a scenario like that is a tough one, but it's quite common in metabolite mass spec. So for this, one common solution is to use the square root of intensities instead of using intensities themselves. This has the effect of curbing down the most intense peaks to a much more manageable size while having a relatively light effect on the smallest intensity values. So it creates a situation where we place less emphasis on matching only the most intense peaks. Okay, what if we have some sort of unknown structural tweak, like a methylation or some other type of adduct that's taken place? In a case like that, we need to be able to match to all library spectra that fall within some maximum tweak size. So if we're allowing for a change of up to, say, 180, we're going to have to consider a far larger number of comparisons than if we have a very small mass change that we're looking for. That was the hybrid search that we were talking about just a moment ago. So there are plenty of really great metabolite interpretation databases out there. NIST is just one of them. So I've already explained that you can buy this and have it for use in-house. METLIN is a really interesting library, and I think it helps to illustrate that there are very different mindsets about open library construction and commercial library construction. So we've already said that NIST is not a commercial library, but it's a government program that sells its data, right? So buying the disk or getting access to the download of it costs you money. METLIN is an academic database, but it was generated in connection with a whole bunch of chemical manufacturers. So the condition under which these metabolite standards were made available to the lab that produced METLIN, Gary Suziak's lab, specified that the data could not be made available freely. So the METLIN website has access to a tremendous number of metabolite tandem mass spectra, but you can't download the whole METLIN database and use it on your computer. You must use it through their web interface, which means that you need to have some trust about what happens to your data and so on. And these things, I think, are pretty well cared for in the METLIN environment. Okay, there was a big resource that started as MassBank in Japan, a really great database, very much focused on open data. There's now a mirror of it here in Europe, I think massbank.eu, created by Stefan Neumann's group. MassBank is really cool, and there's even kind of an interesting side project called MassBank of North America, which has added a whole bunch of things through Oliver Fiend's group. So they're effectively the Japanese and European mirror sites, and then there's the MassBank of North America that is a separate project. And Lipid MAPS is definitely worth talking about, because if you're dealing with tandem mass spectra of lipids, you want to be sure that those are well represented. Lipid MAPS has a very good answer for you. Now, I would like to take you through an example of what it looks like trying to identify a metabolite. I'm going to consider for just a moment, we have this one MS, and we want to identify it. So we're going to use an example posted by Stefan's team that goes through this process in video. All right, so first we're going to enter mass to charge and intensity pairs, and then use the Find Metabolites button. Takes a moment to do this searching. Again, this is all happening through the web, using computers at Scripps Research to do this this type of identification, this matching against the spectral library. And back comes the result. We have a structure drawn for it, and we have these little mirror spectra that'll show up in just a moment. Okay, so when you click on these, you want to know how well does what you saw match what they saw. So what you're seeing in the one case, up top is the observed set of intensities, and down at the bottom are what appeared in the reference spectral library. So it's a very quick way to visually assess, does what I observed match what the spectrum library says should be there. Okay, so that's a pretty quick example, but it is it's free to set up your own account on METLIN, and if you're dealing with spectra of LCMS MS or GCMS data, this is a very valuable workhorse for you. I wanted to mention MassBank again. Here's massbank.eu giving us some results back. Again, we're getting this mirror view where we have the observed fragments up top and the reference library down at the bottom. And we're seeing, in this case, a molecule that shows up in my favorite beverage, tea. And so the catechins are different types of phenolic compounds that give tea some of its vum. So in this case, we have a list of peaks that we saw in our mass spectrum. We pass that to MassBank, and it's able to produce this list of putative ions in response. This is great if you're going for what does this individual spectrum represent. It's quite a lot more difficult, though, when you're trying to do this identification across thousands of MSMS spectra. We'll talk about an option for that in a moment. But I didn't want to leave Lipid MAPS behind. The Lipid MAPS structure database is your way to be able to say what fragments should be seen if I've blown apart this particular lipid. And then you can do that type of comparison yourself. I did some searching on the Lipid MAPS website to see if I can submit an LCMS spectrum and get back an identifier. I didn't immediately see a way to find that, but it may exist. It may just be that I'm not familiar enough with their website to do that. But critically, I think it's really important that we talk about how do we totally automate the process of identifying everything in a raw file, or in a WIF file for that matter. So in this case, we don't have one spectrum of particular interest, we have thousands of them. We want to identify all of them. The reality is that if you're dealing with something as messy as plant metabolites, it's quite likely that some of the metabolites you'd like to measure are not in the reference library. If they're not in the spectrum library and you can't match them by, say, a hybrid search, it's going to just go unidentified. So in this case, I'm showing a result from GNPS. This is a big natural products service made available by UCSD. I've got the link to the workshop up here. It'll probably be a lot more legible in the PDF you can click on in the notes for this YouTube lecture. But in this case, I want to spend just a moment talking about this. Now, this is a very unusual image. In this case, we're looking at a spectral network, which is to say the software is able to recognize relationships, structural relationships, among the compounds that you measured experimentally. So if I have this metabolite and I have another metabolite that differs by just a methyl, well, the software can recognize that the fragment ions between these two have been shifted in some places by 14 mass units, but that they're otherwise quite similar. So it can create linkages among experimental spectra that represent structural relationships. And some of these can be recognized through canonical spectral library search. So you may not know exactly what this gray blob is, but the fact that it has an arrow linking it to a blue blob tells you, oh, the blue blob was identified in the spectral library. So this is some sort of chemical derivative of that. Spectral networking is very, very powerful in helping to leverage the information from spectral libraries to closely related compounds. Okay, and you can find more information about that in Ming's paper from 2016. He now runs the GNPS 2 service over at UC Riverside. So both UCSD and Riverside have software of this type set up. Okay, so GCMS has been around forever, and yet it retains its key place in metabolite identification because these very robust instruments produce data that lets you identify a huge variety of metabolites based on the spectral library matching. It's quite a complete tool flow for molecules that you can deal with in GCMS. If you only have an intact mass for a metabolite, it's probably not going to get you an identity. It may be able to get you to a handful of compositions, of chemical compositions, and yet having fragment ions from it is going to be a lot more helpful in nailing down that identification firmly. There are quite a number of all-in-one metabolite spectral libraries. These are not necessarily focused on plant metabolites or human metabolites. In some cases they are on humans, but generally the spectral libraries for metabolites try to capture all metabolites of all living systems. You can only go so far with that. We're never going to be able to say we have the complete spectral library of every chemical compound in every living creature. It's not a reasonable expectation. So if you're dealing with something like lipids in particular, it's probably going to be of great benefit to you to use a lipid-specific spectral library, not to use those that are attempting to identify just anything out there. And frankly, it doesn't make a lot of sense. If you have mass spectra of lipids, why would you compare them to spectra of carbohydrates? Doesn't necessarily make sense. And of course, the last bullet point is kind of a point of frustration for the field. Being able to identify an individual MS is good. We like to be able to do that. And there are some pretty good methods for it. But as we try to scale this to thousands and thousands of tandem mass spectra collected in raw file after raw file, doing it one by one is not going to be tractable. You're really going to need an approach that is able to identify all of the spectra insofar as they have analogs in the mass spec library. But there are problems that come into play with this, such as controlling false discovery rate. You don't want to get into a situation where you simply say, this is the best match I've got for this spectrum, I better trust it. You shouldn't do that. You really need to have the evidence of the fragments, for example, and these visualizations like the mirror plots that help you to confirm that these fragments seem to be very specific to this and only this metabolite before you go on publishing on the Nature of Science or whatever. Okay? So automating this analysis at a large scale is something that has been relatively slow. Largely this is because of the great diversity in matching quality that occurs for metabolites that generate just 2 or 3 fragments or those that generate dozens. Okay, that is the end of the talk. I hope this is useful to you. If you have some questions that you'd like, try to make comments on YouTube here and I'll try to get to those. I gotta say, I don't even notice in many cases that there are questions raised in YouTube comments. So feel free to email me. My address appears down here. And I will try to do my best to answer. I frankly shudder a little bit when it comes time to answer email because there are a lot of them. So I'll try to do my best for you, okay? Great, thank you very much. And I hope to see you the next time we post a new video. Thank you.